All right, everybody, welcome back. When last we were chatting, we were talking about the idea of the law of reflection. The angle of incidence equals the angle of reflection. Depicted here in the animation, the two angles below in the Greek letters are alpha and beta, and those two angles are equal. They are measured with respect to that perpendicular or so-called normal line, normal to the surface of the mirror. Now, we have been talking really about visible light, but everything I'm saying does apply to all forms of EM radiation or electromagnetic waves, as long as you have the right type of surface. For example, visible light reflects really well off of glass. It reflects especially well off of glass with aluminum or silver on it, what we know as mirrors. Doesn't reflect terribly well off of, let's say, a brick wall, so where it's mostly going to be absorbed. On the other hand, radio waves will reflect really well off of satellite dishes, but maybe they won't reflect so well off of a human being, where they might just pass pretty much right through the person. So just keep that in mind. Reflection is a universal phenomenon, does apply to all forms of electromagnetic radiation, as long as the thing upon which it is reflected is the right size. It's the right order of magnitude. Again, X-rays, for example, they reflect really well off of the right type of stuff. They don't reflect super well off of most things. They'll pass right through most things, but you get something that happens to be the right order of magnitude, particles, for example, and they will reflect right off of them and scatter almost like billiard balls. Okay. Now, for the remainder of our chat, let's talk about light hitting curved surfaces. This is where it gets a little bit tricky, because it does start to seem like the law of reflection isn't so very much like a law. But in fact, it is actually the exact same thing. So, let's look first of all at the case of concave mirrors. A concave mirror, that's the one that's like the inside of a spoon. The curved inside of the spoon, not the outside of the spoon. So, for this to make sense, you kind of have to think of a curved surface as being an infinite number of an infinite set, or a huge number of very short straight lines. So, you have a light that hits a curved mirror. We kind of imagine that at that instant, at that tiny little part of the mirror, we imagine that itty bitty little part there as being flat. And then the light is going to bounce off of that itty bitty little part according to the law of reflection. So, again, take a look at this. The light goes in right here, and if you can imagine the little part of the mirror being flat right there, almost what you might think of if you were a geometry fan as a tangent line, then the light bounces down like it's shown below. And I'll show you this in a little bit more detail in another slide. So, in the figure up top, the light ray hits the concave mirror. Down below, we can see how it reflects according to the law of reflection. It hits the curved surface at some kind of angle, as we're measured with respect to a normal line. That normal is basically perpendicular to the surface at that point, and then the ray reflects accordingly. Here it is in better detail, however. So now you can see what's going on. Here's your light ray. It comes over here. Now, I drew this line in here to represent a tangent line. Tangent line, you might know, is a line that touches a curved surface at exactly one point. So we then draw our dotted line as the normal line. Light goes in here, bounces, and comes down that way. This angle is equal to that angle. Angle of incidence, angle of reflection. So you kind of have to imagine that then this happens, oh my gosh, millions more times. And we can start to see what goes on with curved mirrors and how, in fact, we can actually get light rays to converge and form an image. So more about that shortly. Okay, are you with me so far? Now, here it is in reverse. If you look down at the bottom where light rays are coming in right there, or one light ray comes in there, here is your tangent line. The dotted line being the normal or perpendicular line, and the light ray reflects like so. So you can see there's a bit of a reversal going on. The light ray is reflected up from the bottom, or it's reflected down from the top. Let's take a look at that with a little more detail. We're going to go back to our light playground. So this is what we looked at last time. Let us reset this. And I'm going to now start with a beam. there we happen to have a beam. Actually, we'll make it just 2 rays. And I'm going to use a circular arc. This is a little bit tricky to draw. Oops. Sorry, I actually wanted, there it is. So right away you can see something going on. Look at these 2 guys hitting right there and how they happen to reflect. You might also notice that they cross at a point. I'm going to go back here to a beam. Now look what's going on. These light rays come in, and they actually are crossing over with these other ones. That is not by accident. In fact, if this is a well-designed arc, then they in fact should meet at a point here. Now, there's a caveat to this. These light rays need to be parallel to each other. If they're not parallel to each other, then they're not going to actually cross at the same point. Let me show you that right now. So let's take I'm going to actually start with a circular arc. Whoops. Let's go. Maybe I can drag that down a little bit. Like so, and clean this up just a bit. Okay, now let's take a ray. Ooh, interesting. But let's kill that one for a moment. There we go. There's a ray right there. And a ray right here. So, right here is where these 2 guys cross, and as it turns out this one, because I made this a circular, almost a semicircle, it does hit at this point. Most mirrors aren't like that. Most mirrors just have sort of the inner third. Most curved mirrors would have like the inner third of this, so you don't get that sort of effect going on right here. So, maybe I could clean that up just a little bit. There it is. Okay, that's a little bit better. All right, so there you have it. Now, how about if I take, oops, let's get rid of that. Now let's go with a beam right here. What do we have? This light coming in and converging at a point. Now, I've got a whole mess of stuff going on here, so let's just focus on the one thing, go to the circular arc. Oops. It's a little bit tricky to play around with this. I encourage you to play around with this yourself. Let's go with a beam. And right there, you can see all these rays coming in. They're parallel to each other, and then they meet at this point right here. So let's hold that thought for just a moment. So, if you do have many rays of light, and if they're parallel to each other, then they converge at a particular point. Now, we call that point the focal point, sometimes called the principal focus. And the distance from the center of that curved concave mirror out to that principal focus is known as the focal length. Now, when you get light rays that converge at that point, if they come from some thing, maybe they come from outside, they come from a tree or something like that, or the sun, whatever, if they form there, you're actually going to get an image at that point that we call a real image. It's actually a real image. Now, believe it or not, you've seen this before, sort of. If you've ever seen satellite dishes, and I know you have, they have a very particular shape. They are shaped, usually they're mesh or they're solid, but because they only have to reflect radio waves. The light rays reflect to a point. Those light rays are coming from satellites, from their communication satellites that have been used by whoever the parent company of the media happens to be. And they're sent there, they make it to your satellite dish, they go into the feed horn, and they can be decoded by your cable box. And of course, most of that stuff is now sort of, it's gone by the wayside with internet and whatnot, but you still see satellite dishes around. DirecTV, or you might see big old satellite dishes still up in some people's yards. The same idea applies here. That's just going on with radio waves, but here we're talking about visible light. Here it is animated. There you go. Look at that. It's beautiful. And this would work with water waves, too. If you happen to have a curved surface and water waves are aimed in that way, then they're going to converge at that so-called focal point. Now, what is a focal point? Well, here's where it starts to get a little bit messy. Now, the focal point is where the light rays converge or meet after hitting the mirror. Down here is where they converge. I apologize. This gets cut off a little bit here. It is, of course, related to the curvature of the mirror, and only curved mirrors have focal points. Remember, so far we're only talking about the concave types. The distance from the center of the mirror to the focal point is called the focal length or the focal distance. If you've ever played around with cameras before, you know that this is related to what's going on with lenses, if you've learned about focal lengths. Images only form at the focal point, but that's if the rays are initially parallel. And that happens to be more of a rare case. So light rays are only going to be parallel if the object is really, really far away from the mirror. So normally images form in other locations that are not the focal point. They're normally forming at some other location entirely. If indeed they form at all. In fact, if you put an object at the focal point, no image will form. If you put an object within the theoretical focal point, no real image forms. Only virtual images form. Now, I've used these two expressions, virtual and real images, so let's talk about these a little bit more. Oh, here it is in some more detail. The focal point, again, is where the parallel light rays converge or meet after hitting the mirror. But this is important. They have to be parallel light rays for them to meet there. That is what actually defines a focal point. It is the point where parallel light rays would meet. If the light rays aren't parallel, which basically means if the object is not all that far, but rather fairly close, maybe within, between 1 and 10 times the focal point or so, focal length, then the light rays are going to focus elsewhere. If at all. In fact, if you are within the focal point, they will not focus. You will not get an image. So, now curved mirrors. Let's talk about convex mirrors. Here you have a convex mirror. Now this is a little bit stranger. So parallel light rays, again, we're going to start off with. They're going to hit this mirror and they diverge, so you do not get a real image right here. However, it appears as though the light rays sort of emanate from back here, and that tricks your eye into thinking you have an image inside the mirror that we refer to as a virtual image. Now, you're actually much more familiar with virtual images than real images, to tell you the truth, because every time you look into a flat mirror, you see a virtual image of yourself. Think about it. Think about looking into a flat mirror. You see yourself behind the glass. That's a virtual image of you. You could not put a piece of paper somewhere and get an image of you from that mirror. It doesn't work that way. The light rays don't converge from that flat mirror. Now, here's the convex mirror animated. So imagine we've got light rays that are going to come. There's your object. One light ray comes in. Another light ray comes in, reflecting back that way, but it makes it seem as though they emanate from back here, tricking your eyes into thinking that you have a virtual image inside the mirror. Think of a convenience store mirror or a corner mirror or something like that you're trying to use to see around a blind corner. Now, the types of images. Let's get into the details of this. First of all, a real image. This is a concave mirror right here. The light rays the light rays from the candle are hitting this mirror and they are converging onto this screen right out there, which is beautiful, if you ask me. And that is an upside down, larger image. It doesn't have to be larger, but it is in this case. The flame is the object and the real image is projected onto a screen. That is a real image. You literally, if you put your hand there, you could actually feel the warmth of it, because not just the visible light rays are reflected, also the infrared. Here's another thing that we can say about real images. They can be projected onto a screen or even just into the air. Easy to see if you have a dark room. They're generally upside down. They can be bigger, smaller, or the same size as the object. All of that can be calculated. And as the distance between the mirror and object decreases, the distance between the mirror and image increases until you get to the place where the object is located at the theoretical focal length of the mirror. Now, virtual images, these are the cases where no real images form, but rather you get an image appearing inside of the mirror. We call it a virtual image. It appears to be inside the mirror and cannot be projected onto a screen. And this is very much like convenience store mirrors or side view mirrors in cars or those blind spot mirrors. And here's an example of a virtual mirror, a virtual image in a mirror right here. Now, we're going to talk a little bit more about how these images form in our very next slide.